Okay, we're back. So let's continue to where we stopped. So now we say that we are dealing with everything as vectors. Okay. So now we say that each of these points has magnitude and has direction, and the components of each of these points consist of the direction as well as the magnitude of that vector. Okay. For example, we are saying if this was 5, okay, this was 5, and this was -1, -1, and so there is a vector that defines that point. Okay. That is the vector of 5, x1, and -1 for x2. Okay. So all of these points are vectors. Okay. Now we are going to classify all those points, all those vectors. Okay. How? Well, we are saying that we multiply the weight, that vector multiplied by some weight plus a bias will result into some value f of xi. And that value will give us some information. So it is 0. Yes, Jason. Yes, Jason.
Microphone.
My microphone.
Mr. Khositi is having network problems. He's with me here.
Was it Chile? Where? Can I see him?
I'm here.
Where?
I'm here, sir.
With Jason. Okay.
Yes, next to you, sir.
Okay. Okay, there you go. Okay. So what we are saying is that there is a function f of xi. For every xi, we run this function, and then we are saying that in that it will give us the classification. It will give us some number pertaining to that vector. Okay, pertaining to that vector xi. If that vector belongs in some region to the left of the separation line, we say that the value of that is greater than, the value of f of xi is greater than 1. Okay, in this case, greater than 1 in that side. It should have been greater than 1. Okay, never mind. So in this case here, greater than 1 to the left and less than 1 to the right. Okay, so any point you evaluate into that function will give you some value. If all the points are correctly classified, then to the left of the separation line, you get greater than 1. To the right of the separation line, you get less than 1. On the separation line, you will get a 0. Okay, you'll get a 0, and on the margin of this, we call it support vectors. That means the vectors that are closest to the separation line. Okay, on the margin, on the support vectors, if that vector is called a support vector, that means that vector is closest to the separation line that defines the margin of your separation. Then we say that the value of that f of x on that support vector is +1 in this direction and -1 in that direction. Okay, that's how we define the support vectors. Any questions on that? Then we can discuss about the margin. We are saying that this margin can be, the value of that margin is the maximum or the optimal value of that margin is 2 divided by the norm of the weight. Okay, I mean the value of the margin is that 2 divided by the norm of the weight or the magnitude of the weight. And to maximize our margin, therefore, we want our weight to be small so that we can maximize the margin. Okay, any questions? Is that all clear? I guess that's clear. Let's continue. We didn't do presentation. Okay, now, this was what we did. Now, let's go. So now we would like to optimize SVM. So how do we optimize? To optimize SVM, we want to maximize this margin. We want to have a much bigger margin so that for any data that is not seen, then we can allow perturbations of input data. Okay, so it will be able to absorb uncertainty in the data. So we can formulate, we want to maximize. So this is how we are going to optimize SVM. We want to maximize did I mention to you how did we arrive at this here? Not, okay, I should be here. Okay. So to tell us how did we arrive at this 2 divided by the norm of the weight for the margin, we'll consider this. Okay. So we consider that on the line, on the separation line, your WTX plus B is equal to 0. This we know. Okay. Multiplied by some number, it will remain 0. It doesn't matter. Now we say that on the line, okay, on the line we have this plus 1. On the line itself, this is plus 1. And on the line of the blue line is a plus 1. On the line of the red line is a minus 1. Okay, so let's write it down. Okay, so this is your vector on the positive, support vector on the positive, and your support vector on the negative side. Okay, so that's what it is here. You have a positive support vector that is plus 1 and a negative support vector that is minus 1. Okay, so we draw it. Okay, so now this vector, that vector is what? That vector is this vector minus that vector, isn't it? Isn't it? Yeah. So now we say, yeah, this vector minus that vector. Okay. So now we are saying that in order to consider this margin, we take that vector, X, the support vector, whether positive or negative. Okay, let's just say positive vector. Okay, sorry. Minus the negative vector, negative support vector. Okay, that's how we get it. Okay, now in order to get the magnitude, okay, we divide it by the norm. Okay, anyway, let's consider first. Okay, in order to do that, we consider the values of this, the value of this, the value of the function here. So the value of that function for the positive direction is, let's consider the positive WT XI, no, not XI, but X positive, okay, plus B is equal to 1, and then WT on the negative direction plus B minus 1. Okay, now subtract that. Okay, somehow because this distance is this vector, you minus off the 2 vectors, then divided by the norm. You take a value, you take negative value divided by the norm, or you take the norm of this vector that you take the norm of that. Okay. And now, considering that, okay, using the same principle of taking the minus, taking the negative, you're subtracting those 2 vectors. So here we subtract. We know that this vector here, we subtract that vector against that vector, will give us that value. Okay, so now we say that this is WT X on the positive side. Okay, these are the same, so they cancel. Minus WT on the negative side, negative support vector, is equal to 2. There you go. Okay, so now this is the vector. Okay, now we normalize. This is the two vectors. Okay, in this case, because this results into 2, so now we normalize. We normalize the value of your weights so that your weight now goes from 0 to 1. Okay, the norm of your weight goes from 0 to 1, so we divide it by the weight. Okay, so now what we are saying is that this equation here will give us the value of this margin. So that is equal to 2 divided by the norm of W. No matter what your W is, that is always the margin. Okay, so now if you want to maximize the margin, therefore we want to minimize your W. So that's how this value is taken. Any questions? That's how this is taken from. Okay, okay, let's continue. So now we want to maximize, because we want to maximize the margin. So this is the margin, 2 divided by norm of W, the normalized margin. We divide it by the norm of W. So we want to maximize this one subject to the function of evaluation, the function of f of xi. That is, it can be greater than 1 on a certain, when yi is positive 1. It can be less than 1 when yi is minus 1. For all I from 1 to n, where your n here is the number of points. Okay, you have to run through all the points in the data. Okay, or equivalently, we want to minimize. So in this case, because we want to maximize this one, if you minimize your W, then that means we can maximize the margin. So minimize the margin subject to the same constraint, but now we mentioned this one already, that if this function f of xi multiplied by the classification, it's always greater than or equal to 1. Okay, because they are correctly classified for all I greater than 1. So do we agree here? So now we say that it is quadratic optimization because it is quadratic to the second order. Okay, and subject to linear constraint. Linear constraint because our constraint is linear. Okay, and that there is a unique minimum. Okay, this is a linear equation. Okay, even if you multiply yi here, that's a linear equation. So subject to, that's why this condition here, this optimization equation has a unique minimum. And so it will definitely converge to a number W, where that W will be the maximum margin. Okay. Any questions? Any questions? Why do you think this is squared? Why do you think this is squared? Will it make a difference if you have a square here or no square? Why is there a square there? Aune. Why do you have a square? Okay, let me delete everything. There's a square. At the bottom here, there's no square. Here, there's suddenly a square comes out. Are they equivalent? They're not equivalent. Do we need a square? And why do we put a square? This is the good thing about if you go higher mathematics. It's not just all about computing. It's more of analyzing, because we're dealing with certain maybe practical applications. And in some cases, we know where we're going. We know what to extract in that computation. And you just want to put certain things there to make our life easier. And it doesn't make changes in any of our initial, purpose. Just like you come here, your major purpose is to finish school, yeah? But along the way, if you have fun along the way, if like, for example, you go to Wamzito, it doesn't change you from, maybe it sways you a little bit, but then having fun as a student can be part of the life of a student, but it doesn't mean you are swaying from the original purpose. So the same thing here, we are adding certain things. It sways a little bit, but still it goes towards the same purpose. Are they equivalent? Why is it? How come I don't see people's cameras? Kevin, I didn't call you today.
So, I can't show my camera. I'm not feeling well.
Yeah, it's okay. If you cannot show your camera, just talk. Come on. Tell me, are they equivalent?
I think the equivalent.
Yeah, of course, because it says here, or equivalently. For sure, it is equivalent, yes. But why? Why would they be equivalent when there's a square here and there's no square there? And now it's the denominator, that's the numerator.
I think the square part is the one that removes the negative part of the equation that's above.
No, there cannot be negative here. It's a norm. Norm is not negative. Norm?
Like the negative and the negative.
Huh? You already
The
said.
negative.
That's the norm. Square root. W multiplied by itself. Square root. There. You see it now? Kevin, do you see it now?
Yeah, I can see it, but I have no idea.
So, why? Why is there a 2 there? Why do we need to square it? It's just very simple.
To remove the square root.
Yes, to remove the square root. Yes. So when we are dealing with this one, there's always a square root. Okay. So what we're saying here is that when you maximize 2 over W, norm of W, so we want to get rid of the W at the bottom as the denominator. So if you make it the numerator, to maximize this term, we need to minimize W. So now we put here, minimize W. It's fine. It's the same. It's equivalent. Minimize W. So now, if we square the W, does it make sense? I mean, does it still the same function? Is it still stay, even if you put a W here, does it change the fact that we want to maximize this? It doesn't. Okay. Still, we want to minimize. Whenever you minimize W, if W is minimum, you square that, still it is minimum. Okay. So maybe the value will become much, much lesser because you square a very small number. But then, you know, but then still, the fact remains that whatever that value of W, whenever we say this is the minimum W, you square it, it will still be the minimum W. So we will just remove the square root because, okay, because in order for us to get rid of that square root. And so, you know, you can just write this one as W like that, W T times W without the square root, minimize. Okay, subject to this linear constraint. Understand? So now, this is how we are going to do. We want to maximize that W in all our computation in support vector machine compared to perceptron. Perceptron, all it wants is to separate the two. But for SVM, we want to maximize that margin. Okay, we introduced the concept of a support vector, those vectors that are closest to the separation line or separation hyperplane, and then we maximize the distance between those two support vectors by trying to minimize the weight. Okay, W. Understand? So our purpose then for all our exercises in SBM is to look for this minimum W subject to this requirement. Okay, so in this case here, there are some optimization considerations. Yeah, for example, here in this case, yeah, everything is correctly classified, but not really a very big margin in terms of the support vectors from the blue and the red triangles. So now, if you do this, there's a large margin here, yeah, but then this is not correctly classified. Well, I guess we can sacrifice this in order for us to maintain a large, margin. Well, for all we know, maybe this is just an outlier. Okay, so we can do this in order to have a possibly large margin, which is a better solution. Okay, so we introduce the concept. Furthermore, okay, this is just some ways to consider in the maximization problem, or in the optimization problem, the minimization problem of trying to minimize a W. So we introduce the concept of psi. In this psi, okay, this psi will give us some consideration for points that are misclassified. So psi can be greater than or equal to 0 if the point is in between the margin or the correct side of the hyperplane. For example, here is still correct, but closer to the hyperplane, then the psi is between 0 and 1. But if the psi is misclassified, for example, the psi is here for the red part that is already outside of this region, okay, it crosses the hyperplane, it is misclassified, and psi here becomes greater than 1. Okay, so we introduce this psi value in order for us to help in terms of optimization, in terms of the optimization equation. So here we are saying that if psi, we want to minimize psi as well. So if you minimize psi, that means you minimize these things being misclassified. Because if psi is bigger, then this value is misclassified. This point is misclassified. okay, according to some computation. Okay, so if psi is becoming smaller and smaller, or it is 0, it means that it is correctly classified. Okay, and it is not between from here to here, correct classification, not between the margin, the psi is equal to 0. Okay, so here, that's why in this case here we want to minimize the psi for all points. Okay, for every point, if there is a corresponding psi. For all points here, the psi I, the psi for this value, the psi for this, I call it psi, but I think it's C or xi, psi, yeah, anyway. The psi value, the psi value for all of these points that are correctly classified beyond the support vector, the value is equal to 0. And the psi value for these points that are inside the margin, that is between 0 and 1. And that one, for each of these point that is beyond, that is not correctly classified, then there's a psi I that is greater than 0. So each one of these points have a corresponding psi. That's why you have a psi I. And then you sum all the psi's for each point from 1 to n to the sampling size n. And then if the psi is small, that means there are less and less points, or very less points that are misclassified. Now we include it as our constraint, as our objective function, that the psi, summation of all the psi for all points to be minimum. And then we include it in our constraint as well, that this psi is corrected. Okay, now is greater than or equal to 1 minus the psi. That is, this is a correctly classified one, but this psi can have some value between 0 and 1. Okay. So now, so they have a regularization parameter. So we modify. So from the initial value, the initial equivalent optimization equation is like this. Now we introduce the concept of the psi for misclassified data. Then we now have a modified optimization problem or optimization condition, where you minimize the W, okay, the norm of the W, plus now the psi of the misclassification. And then we have the multiplication. This multiplication remains minus the correction for the psi that are within the margin. Okay. So now, okay, we can go through all these. The equivalent of this equation, okay, of this constraint, is that your psi, the maximum, we try to maximize between 0 and some value of 1 minus the correction of the psi that is not of the classification of the psi. So if psi is correctly classified, this is becoming 0. And if psi is not correctly classified, then this one is a positive number, okay, or some number, okay, positive or negative number. So now, if this value is greater or something that is different than 0, then we consider this as a loss function. So the regularization is this part, and this is the loss function. So for all of you who will be going through, for others will be, not all of you, for some of you who might be interested into a deeper consideration or studies of SBM, this is what we are going to do. You're going to consider a loss function as well as this regularization. Okay, I mean, it's something that we need to know, so that later on it will be easier for you to understand. But anyway, so this loss function, if we are saying we consider this loss function, and this is the optimization condition, the loss function, you will have if your yi f of xi is greater than 1, this is the point that is outside of the margin, no contribution to loss. Okay, greater than 1. Okay, so if this is greater than 1, so that means that 1 minus, so this is a negative number. Now, if your point is on the margin, so that is equal to 1, then it will become 0. Okay, and now if your point violates the margin constraint, that means this is less than 1, so it becomes a big number, a big positive number, and it violates the condition, and so it contributes to the loss. Okay, so that's how the loss function is being interpreted. So here, this is the one that your value, it's supposed to be Okay, here you are going to be with no loss. It should be, this one is greater than 0, so that means the greater than 0 becomes a negative number. So here, okay, if when you're here, you're negative, so that means that, yeah, this one is negative. So what is it? Greater than 1, then no loss. Yeah. So greater than 1, no loss. So loss function is 0 here. But when you are at 0, at 1, then still no loss function. At 1, no loss function. But when you're less than 1, that violates, then this is the graph of your loss function. It could be when you say maximum of this, or it could be approximation of 0 and 1 loss, then this one, but then you have a hinge function. It can go, as this one grows bigger, then you can have a much bigger loss. Okay. Okay. So anyway, so I want to just start by saying that this is the optimization is it does have a unique solution. It is convex. Convex meaning, okay, it's a convex problem. Graphically convex. This is convex, and this is not convex when you have many. Okay, many you have a local minimum. When you have convex, you only have one minimum for the entire function. Okay, so what we are saying here, that this is a convex function, there will always be a minimum. Okay, so there will always be a minimum. We are trying to optimize SVM. That means we always converge to an optimal value of W. Okay, so I think I have to stop there. And to consider that here you have a loss function, in this case of the Lagrangian, the hinge loss, the Lagrangian with respect to the change of W, you have this loss function of 0, and you have this loss function when you are at this side of this graph. So we are considering here, when we consider finally, okay, this is the final update for your W. We went through all these equations to say that the final update of your W, in order to minimize this function, okay, it is a function of the Lagrangian function, as well as your weight, the norm of the weight. And so if you take the gradient of this function, it will be a function of the weight plus the gradient of the Lagrangian, which can be simplified into this weight, this part, this part, okay? And then when your yi in this Lagrangian gradient, when your yi f of x is less than 1, that is misclassified, then you have a correction factor. If it is not misclassified, then you correct your weights according to this equation. Okay, so now with all those, with all these analysis that was computed, we now have two approaches in terms of updating your weight W. So if there is a misclassification, you correct that with this function yi times xi. If there's no misclassification, then you just proceed with this function by updating your weight W. Okay, and so we continue. I'm leading towards the computation of your weight W with this function here. That's why it takes me a lot of pain to go through these equations, so that you'll understand why what we are doing to maximize to optimize SVM. Okay, so I want to leave you with these equations, that the W can always be written in a linear combination of the training data. So this W can always be written as the sum of all your X's of the training data, the n samples of data, multiplied by the classification plus some value alpha. Okay, alpha can be some learning rate or something. It could be yeah, a correction factor or some learning rate. Okay, so now, okay, we have to consider this when you are considering. We have to consider this equation as a way to check the value of your W, and then we continue that there is a primal and a dual. Now this is not there's some way of writing, okay, in terms of the dual version. This is where this that your W can be written in this form. Okay, so now your W can be written in that form. Okay, just like what we are saying here. Okay, your W, instead of WT of X, you can write your W in terms of going through all the training examples multiplied by the support vectors. Okay, in this case here, this is a support vector going through all the support vectors multiplied by the X. Then you can write this as your f of X function instead of just this function that we normally deal with. Okay, so this is important because now later, when you look at, when we compute the support vectors, this is what we need. Okay, to solve for your W, we will look at this function. Okay, now I think we need to stop there so that later we will understand. I will discuss this function of the kernel trick after the linear classification. Okay, so here's an example. I want to leave with this example. So in this example, we have two types of two groups, two types of data, the red data and the black data. So the red one is to this side and the black data is to that side. Now we have three support vectors. And in these support vectors, these are the coordinates. Okay, so now we augment with a bias. Okay, because we want to write it in the same form as before. We augment with the bias, we make one of those support vectors. And then now this is what that was what I was telling you, that we can write the optimal weights to be multiplied by that support vector multiplied by that classification times some value alpha. Okay, so when we consider the support vectors, this is the support vectors multiplied by the alpha. Okay, so now we are saying that W times a support vector that is plus or minus 1, and then we can write it in this form. So, okay, I think it's almost time. So what we are saying here is that this is the final equation in order to solve for our W times W. We will look for this value. We will look for this value W. We will look for the value of this one. Okay, and then before we reach there, we have to consider this computation. So now in this case, our N is the number of support vectors. So in this case here, there are three support vectors. So okay, consider this equation, alpha times Si and the support vector Sj, the other support vectors. So here, alpha times S1 plus the other support vector, okay, S1, and then the next support vector, alpha times S2, and so on with the same support vector, and then alpha S3 with the same support vector. And in this case, this is the classification of that first support vector. So S1, the classification is -1, okay? And then for S2, the classification is -2. Again, you multiply this with the corresponding all the support vectors. And then for S3, the classification in -1, then you multiply with this one with the corresponding support vector in this equation, alpha times Si and the corresponding support vectors. So Si, go through all the support vectors for this J support vector. So the same thing here. So go through all the support vectors multiplied by that particular support vector with the equation with equal to the classification. And then you multiply with all support vectors with the next support vector with that support vector's classification. Again, we multiply with all support vectors with that support vector's classification. Now, this is, okay. Then we substitute the values, and now it can be simplified in this form. And so this is a 3x3 matrix, okay, where we can solve for the alpha 1, alpha 2, and alpha 3. So, okay, once you solve the alpha 1, alpha 2, and alpha 3, now we go back to this equation here. We can solve the weights by that alpha. Okay, so now once we solve the alpha, alpha times the support vector is equal to the weight. So alpha 1 times first support vector, alpha 2 second support vector, alpha 3 times the third support vector. And so now this is how you solve for your W. So the W1, this is W1 and W2, and this is your someone is calling. This is your bias. Okay, the bias is -3. Any questions? Okay, go through this example. I mean, this example is linear. Okay, that's why it's easy. So for all linear equations, all we need to do, for all linear classifications, all we need to do is consider these two equations. Okay, they are created based on the dual. This one, we solve for W using all these optimization problem. So now, because these are linear classifiers, we can simplify all the necessary optimization problem, the optimization equations there, we can solve using these equations. So all you need to do is classify that support vector times the alpha and solve for the alpha. And then once you solve for the alpha, multiply it with each alpha corresponds to a certain support vector. And then you can find your W. The same way as in this equation. Okay? And then that's it. You can solve, once you solve for your W, you can check this. Okay? Later we will check this and see that they are correctly classified. Okay? Then next we will go to the solution when you cannot linearly classify them. Okay? We'll stop here. Any questions? Jason, you.